Hello everyone. Okay, so in this video we are going to learn about a new application in differential equations. Okay, so the application is about mixing problems. So what is a mixing problem? Think that you have a tank and this tank is filled with water or some kind of a liquid. Now what you're going to do is you're going to input water into the tank, and at the same time you're going to take water out of the tank. Okay, so there's water in the tank or some kind of a liquid, and you input liquid and you take out liquid. Okay, great. Now let's say not only water, there's some sort of a pollutant or salt present in the tank. Okay, or it could be the case that there's already salt in the tank, okay, dissolved in water, or it could be the case that salt is coming when you pump water into the tank. So really we are interested in we want to see what's going on with salt. Okay, so let's say A is the amount of salt that's present at time t. Okay, so A represents the amount of salt that present in time t in the tank, because the amount of salt is going to change with the time, right? Because you're going to pump water and at the same time you're going to take out water, so the amount of salt is going to change. So A is the amount of salt. Units are very important in this lesson. Okay, so the amount could be represented by grams or kilograms or pounds, right? So those are the units of A. Okay, all right, so A parenthesis t means A is a function of t. Okay, right, t is time, so time could be seconds or minutes. So those are the units, potential units for time. All right, great. Now let's try to write down a differential equation for this scenario. So we are really interested in rate of change of the amount of salt in the tank. So that's dA over dt. Okay, rate of change of amount of salt with respect to time. So simply the theory or the idea here is the rate of change of amount of salt with respect to time is actually the rate that salt comes in minus the rate that salt goes out. So that's the idea behind the modeling. Okay, all right, now even though we say that it is the rate that comes in, it's actually concentration of the incoming salt times the rate of water that's coming in. So that's the actual rate. Okay, so the rate is equal to the concentration of salt coming in times the rate of water that comes in, minus, okay, the rate of salt that goes out is actually the concentration of salt that's going out times the rate of water that goes out. So rate is actually a product of concentration times the rate of water that comes in and out. Okay, all right, so this is how you model the differential equation. This is the basic idea. Now again, units are very important here. Okay, now let's say the amount of water, since we are talking about concentration, we have to talk about volume, because concentration is actually amount, okay, amount divided by volume, right? So that's the idea of concentration. So volume, let's say volume can be represented with the units either liters or meter cube, for example. Like volume means the total amount of water that you have in the tank, so it's a liquid, so it could be liter or meter cube as well. And the amount, of course, it could be gram, kilogram or pounds. So let's talk about units. So units of the left hand side actually is, so this is amount with respect to time, so it could be gram, kilogram or pounds over seconds or minutes. So those are the units on the left hand side. Now the units of the right hand sides are going to be, so units of the concentration is actually amount divided by volume, right? So amount could be these units and the volume could be liter or meter cube, and the rate of water that comes in actually the water, so that's liter or meter cube. Since it is rate, we have to divide by the units of time. Now as you can see, units of left hand side should be equal to the units of right hand side. Now you can see the liter cancel out and you can get the units of amount divided by time, which is same as the left hand side. Okay, so same with this part again. Okay, same copy here for the outflow. Okay, so it's going to be units of amount over time. Okay, units are very important because it's not easy to set up a sometimes it can be hard to set up a differential equation to a given problem, okay, right in this model, but units can help you to set up the model correctly. Okay, all right, now what we are going to do is that actually we are going to solve some problems using this idea that we learned. Okay, so let's look at this first problem. Let's try to solve this problem. Now first of all, we have to set up the differential equation. So the differential equation, it's going to be dA over dt, right? Rate of change of amount of salt with respect to time. Okay, now let's read this question carefully. A tank originally contains 100 liters of pure water. So there are two things that we can extract from here. So what's 100 liters represent? That's the volume, right? So volume is 100 liters. That's super important. That's the amount of water that you have in the tank. That's volume. And pure water means what? So pure water means initially you don't have salt inside the tank. So that means the amount of salt in the beginning is 0, right? So that's the initial condition, by the way. So initially there are 0 kilograms of salt in the tank. Okay, that's the initial amount of salt in the tank. All right, great. Now the salt water with concentration of 2 kilograms per liter is pumped into the tank at a rate of 3 liters per minute. Now we know, so let's talk about the inflow. So rate of change is actually inflow line minus outflow, right? So in the inflow is actually concentration. Remember, inflow is actually concentration times the rate. So the concentration is 2 kilogram per liter that comes in, and the rate is actually 3 liters per minute. Now look at the units now. Now liter cancel out. The units are going to be kilogram per minute, and that's exactly what you have on the left hand side. Okay, kilogram per minute, time amount over time. Okay, so we are good with the inflow. Now the outflow, so and well mixed solution is drained at the same rate. So the water is going to go out at the rate of 3 liters per minute. But what's the concentration that goes out? Well, we don't know, right? Because the concentration of salt or the amount of salt is continuously changing inside the tank, right? Because we are pumping water and pumping out water. So that's important. So really, we don't know what's going on when we pump out. So really, concentration is A, that's the amount of salt you have right now, right? That's what has to go out. So right now you have A amount of salt, divide by the volume. So you have to divide by 100 liters. So this is kilogram divide by liters. Okay, so that's where you need the volume. You need this 100 liters to figure out the concentration of the outflow. Okay. So this is just the concentration. Now you have to multiply it by the rate. So the rate is, it goes out at the same rate, 3 liters per minute. Okay, so liters cancel out, so kilogram per minute. We are good. Okay, we are good with the units. We have the correct units. So let's write down the differential equation now. dA over dt is going to be here, it's 3 times 2, 6, minus here 3A over 100. So that's the differential equation. Okay, and this is the initial condition. That's how you set up a differential equation, a modeling problem in a mixing problem. Now what we are going to do is we are going to actually solve this problem. Okay, so we have dA over dt is equal to 6 minus 3A over 100, right? So how are we going to solve this? What are the options we have? Really, we can use two methods, either separation of variables or integrating factor method. Now let me first show you the integrating factor method, because that's the easiest for this case. So to use the integrating factor method, we have to take this term to the left hand side. So dA over dt plus 3a over 100 is equal to 6. So let me write it like this. Now we have to first find the integrating factor. So integrating factor, to find the integrating factor, you need to find p. Now p is actually the coefficient of a, right? Because a is the dependent variable. It's actually coefficient of y, but instead of y we have a, right? That's the dependent variable. So p is 3 over 100. So the integrating factor mu is actually e to the 3 over 100. You integrate with respect to t. Now not x, because x is not the independent variable here. Here independent variable is t. So you integrate with respect to t. Okay. All right. So the integrating factor is going to be e to the, if you integrate 3 over 100, you get 3 over 100 t. So that's the integrating factor. Now what you do is you multiply the differential equation by integrating factor. So it's e 3t over 100 dA dt plus e 3t over 100, here 3a over 100, okay, plus 6, not plus, equal to, okay, you have to multiply the right hand side as well, 6 times e to the 3t over 100. So you multiply the whole equation by integrating factor. Now you know the left hand side will be or can be written as integrating factor times y, right? Here actually y is a, that's the dependent variable, and the right hand side, that's what it is. So 6 times e to the 3t over 100. Now what you need to do is you have to integrate both sides. That's what you do in the integrating factor method. Okay, so to integrate now, if you integrate here, you know it's always going to be integrating factor times a, right? Integration and differentiation, you can think that they are cancelling out. Okay, so this is what you get. Okay, now if you integrate here, it's 6 times. If you integrate e to the 3t over 100, you're going to get e to the 3t over 100, but you have to divide by 3 over 100. Okay, you have to divide by the coefficient plus c. Now if you simplify a little bit, it's e to the 3t over 100 times a. Now dividing by 3 over 100 is same as multiplying by the reciprocal, right? So e to the 3t over 100 plus c. So 3 and 6 cancel out, so you get e to the 3t over 100 times a is actually this is 2, so 2 times 100, 200, e to the 3t over 100 plus c. Okay, nice. Now we can, to get the explicit solution, we can divide by this e to the 3t 100. So we can take it to the right hand side. So e is going to be, let's divide term by term. So 200 e to the 3t over 100 divide by e to the 3t over 100, it's going to cancel out. So it's 200 times 1. Plus c times c divided by e to the 3t over 100, we can write it as e to the negative 3t over 100. So that's the solution, explicit solution. Okay, now we can use the initial condition. So we know initially there's no salt, right? So when time is equal to 0, a is 0. So a is 0, 200 plus c, e to the, when t is 0, this is 0. So e to the 0 is 1. So 0 is equal to 200 plus c. So c is actually negative 200. Let's replace that here. A is actually 200, c is minus 200, so minus 200 e to the negative 3t over 100. So that's the solution of the differential equation. Okay, that's how you solve it using integrating factor method. So I'm going to do another video. In that video I'm going to show you how we can use separation of variables to solve a similar problem. Okay, all right, so that's how you set up a mixing problem, and that's how you solve it. Okay, so basically remember the rate of change of amount of salt is actually the concentration of inflow times the inflow rate minus concentration of outflow times the rate outflow. That's the simple idea. Okay, all right, so I'm going to solve more problems in another video. I'll catch you there. Bye bye.